Hello and welcome back. We are continuing our conversation around these exercises here with our final example surrounding specific numbers. So here we have a proof exercise. Prove that n squared plus 1 is going to be in theta of n squared. And we're going to go ahead and find all of our handy properties that are going to allow us to do this proof. So let's start by opening up our facts document. Scroll back up here. Now we do have those two different, we are trying to work within theta. And so it is the fact that we're going to work within theta. You'll notice that like not a ton of places actually have a theta conditional. So that makes it a little bit easier to spot where we need to start. So we're going to start right here. We're going to take this property and we're going to say that if f is in theta of g, if and only if, we can also prove that f is in O of g and f is in omega of g. So we need to be able to prove that f is going to be in O of g, and we need to prove that f is going to be in big omega of g. So that means we're going to show that n squared plus 1 is in n squared. And we're going to show that n squared plus 1 is in big omega of n squared. Okay. So these are the two sides of our proof here. If we can prove both of these, we'll have proven the original statement. So let's go back into our list of properties and see what we can find in here. Now, the first one that we can find that's going to help us out is going to be the other property that involves theta, which is this one right here, 5.1. There aren't very many. There's only so much you can do with theta without turning it into something else. So there we go. So for any constant c greater than 0, c times f is going to be in theta of f. This right here, this proof is exactly why we're able to say something like n cubed less than or equal to m times n cubed, right? That c constant is indeed like our m from our more specific proofs earlier on. So what that means is for any constant greater than 0, so perhaps 1, 2, 3, 4, whatever it might be, we're able to say that n squared will indeed be in theta of n squared. Therefore, if we can combine 3.1 and 5.1, we're able to say that because of this, n squared is going to be in big O of n squared. And we know that n squared is going to be, in big omega of n squared. All right, so with these two pieces of information, we can go back to our list of properties and see if we can find a way to actually prove that upper bound, that upper and lower bound. We're going to start by proving this side. Now, one that we've seen in a previous video, if you've been paying attention, is this one right here. The addition one right here. And this one right here. We've actually seen both. So let's start with this one here. Since we said we're going to start with omega. So if we look at the omega, there we go, make that bigger, move it right over there. If we start with the omega side, a reminder, omega is like a lower bound, which means if we add something, we're still going to be above our lower bound. That's no problem. So if n squared is in big omega of n squared, then n squared plus 1 will also be in big omega of n squared. And we can see that we have indeed then proven this side as we needed to. So that side's actually done. That's all there is to looking at that side. Now to look at the big O side instead, we can take a look at our properties one more time. And we're going to use a couple of different ones here. We're going to mush a few things together in order to prove that n squared and the 1 are going to work out the way that we want them to. So let's start by looking at these two right here, 1.1 and 1.2. So let's plop these right over here. Okay, so what can we see from these? When we use these two, what we can tell is that as long as our a is greater than 1, we can say something like 1 is going to be in little o of log base 2 of n. And we can say that log base 2 of n is going to be in n squared. So this one is using property 1.1 and this one is using property 1.2. So by using those two and then by pulling in the transitivity property, I'll just pick it up and bring it in right here. The same one that I've been saying every single day. If A is less than B and B is less than C, then A is less than C. Same thing. If F is in G and G is in H, then F is in H. So then here we can say it follows that 1 is going to be in, oops, I can't just say n squared like that, big O of n squared. It's the set of those functions. So we're able to very easily show the one part of this, this side. So just as a reminder where we're coming from, this right here, I guess I can change colors. This right here is actually showing this part of this function. Now, of course, the n squared part is much simpler and straightforward to show. So we can just sort of say that recall from above that n squared right here is, oops, I can just say is an element of big O n squared. And so then that gives us this part, which means once again, we can use 4.2 one more time using property 4.2. We can say 1 is in big O of n squared and n squared is in O of n squared. Therefore, n squared plus 1 is in O of n squared. And you'll notice that this side shows O is in n squared. Sorry, n squared plus 1 is in big O, and this side over here showed that n squared plus 1 was in big omega. So when we put those two together, I'm just gonna like label them with a heart, with a purple heart, because I'm gonna run out of space and I get very symbolic, and a red heart. Because remember what we were trying to prove? We were trying to prove that we were in theta. So what we can now say is by our purple heart, I should have given them numbers, but I didn't, and our red heart, it follows that n squared plus 1 is in theta of n squared. And there we go. We've managed to prove that correctly. There we go. Apologies for running off the page there. Yeah, so what we've done is we've taken that theta, we've broken it up into the two different sides, here and here. We've proven each of those sides individually. This one was quick and easy to prove thanks to it being the lower bound. And then here with it being an upper bound, we just had to show each of these two pieces separately, which we did. We showed it here to get the 1. And then of course, to get the n squared was quite straightforward. Okay, that's all there is to this one. Going forward, we're gonna do a couple of examples with arbitrary functions that are mapped with arbitrary functions mapping that positive integer space to the positive real space. We're going to go ahead and solve a couple of those in the remaining videos. Thanks everyone, and I'll see you later.